In today's tutorial we will discuss labile oxygen-oxygen bonds. Here we have hydrogen peroxide. The oxygen-oxygen bond is elongated because of the repulsion between the free electron pairs. With iron 2+, it is possible that an electron is transferred onto this hydrogen peroxide into an anti-bonding orbital, further labilizing this oxygen-oxygen bond. We will get to iron 3+ and an hydroxyl anion, and most important, also in solution, a hydroxyl radical is formed. This is called the Fenton reagent. You can also induce the fragmentation into two hydroxyl radicals. If you invest some more energy, this is possible with photochemical irradiation. For this molecule dibenzoyl peroxide, also heating up to above 70 degrees is sufficient for achieving the fragmentation in two benzoyl radicals. This oxygen-oxygen bond is even more labile than the one in the hydrogen peroxide, because these radicals are mesomerically stabilized. Well, you can symbolize that by drawing such a structure with the radical character distributed between the two oxygen atoms. These benzoyl radicals decompose further on into CO2 and phenyl radicals, and these phenyl radicals are those who are the starter radicals, for instance in radical polymerization of styrene, or a radical chain reaction like a bromination with N-bromosuccinimide, for instance. These phenyl radicals are not mesomerically stabilized because the sp2 orbital hosting this radical electron is located perpendicular to the pi system. Instead, a benzyl radical is very well stabilized mesomerically because here we have a p orbital that interacts with the pi system. Thanks for listening.